Part 8, Chapter 28. So, in this particular section, you are going to learn how to analyze a circuit where a capacitor and a resistor are connected together. So, for example, here I have a capacitor which is fully charged, and I have a resistor right there, and they connected in a series and with a switch. So, switch is not on at this point. So, circuit like this is called RC circuit. R for resistor, C for capacitor. Now, what happened when we close that switch? So when we close that switch, all the positive charge from the capacitor will move through the resistor and then come to the negative plate to compensate the negative charge density in the negative plate. So let's see how they can do it. What is the relation between them, between capacitor and the resistor while it is discharging? So to do that, we will use Kirchhoff's loop law. So this is a closed circuit, switch is closed, and this is a fully closed circuit. And since we can we know from just looking at the charges, the positive charge will go out. Therefore, the current along that direction. So I can draw a diagram of a current. But if you don't, that's okay. You can just do any arbitrary direction. It will correct by itself. Now, using Kirchhoff's law, the voltage difference across capacitor, delta V cap, plus voltage difference across a resistor, delta V res, is equal to 0. Now, let's start working from bottom end or the negative plate of the capacitor. If I go from there and cross the capacitor, I raise my potential. So therefore, that has to be positive. And we all know from a capacitor equation that is Q over C. So delta V cap is positive, which is equal to Q over C. Now I come to the resistor. Now I'm going same clockwise direction. Now here I'm going from higher potential to the lower potential because that's how the current is flowing. So therefore, I'm losing my potential. So therefore, it is negative. So delta V raised should be minus I time R using just Ohm's law. So if I have now the equation. Now let's look at the current. So now the current, whatever current we have in the circuit, is due to the decay or the charge is going out of the capacitor. So therefore, we know the current is dq dt, but in this case, because capacitor is losing those charge, so therefore current in terms of the charge in the capacitor is minus dq dt. So this negative sign indicate that the charge in the capacitor is decaying or decreasing. Now let's plug in that equation. So what it will come down to like this. Now to find out the what is the how charge decay as a function of time, you just need to integrate both sides, and you can find that okay, at initially the charge is full on the capacitor is q naught. At some point, let's say it's q. Initial time is t equal to 0. At some time, it's t equal to t. If I do that integration, I'll get the result like this. The charge in the capacitor, this capital Q is the charge in the capacitor, is equal to, it is decaying basically as in an exponential way, is exponential t over tau, where tau is time constant. Tau is basically R time C. So resistor time the capacitance of that capacitor. And of course, it's decaying at starting point at Q0. So let's look at how it is decaying in terms of plotting. So at t equal to 0, it has fully charged. So that's the charge it had. Now, as soon as we close the switch, its charge start moving, it's losing that charge and is decaying exponentially. This is exponential curve. So at some point at time tau, at one time constant, the total amount of charge left in the capacitor is like a 37% of its maximum value. At twice the time constant, it only 13% charge is left in the capacitor. So it's decaying like that. Now, what about the voltage across the capacitor? Or what about the current across in the circuit? So charge, we know it's going like this. Now, using simple capacitors relation, we can transform this equation in terms of voltage um, because in a capacitor Q equal to C time delta V. So at any point, the voltage across the capacitor is basically also decaying at its maximum value, which is the voltage at the beginning of the time t equal to 0. That's the voltage is maximum at that point. It's also decaying as the same manner as charge, because charge is you are losing charge. Of course, your voltage is also going down accordingly. Now the current, we found that current is minus dq dt. So if I do that derivative of that charge, right, that equation right there, and if I simplify or replace tau with RC, simplify that, I will find that the current is also decaying same exponential manner. It started with a maximum current and is decaying exponentially. So if I plot that one, I'll find that current I, it started with I0 and is decaying exponentially at time tau, like one time constant. The current value of the current in the circuit is 37% of the initial value. And if I wait another time constant like twice the time constant at there, it will be like 13% of the initial value, so on and so forth.